Okay, here we go. So, week 2, day 1 continued. If I have been talking all this time about prime numbers and we have a little bit of a definition of a prime number, it's only divisible by 1 in itself. But we may be running into an issue, so I want to make sure to just take a step back. I know that last week I posted the hundreds board in week 1. I'm going to repost it in week 2 so that you can see it, so that you can use it if you need to. In fact, we're going to talk about it right now. So my question becomes, we've been talking about primes, how can I possibly know? And one of the easy ways to know is through the hundreds board. So I posted it, you can grab one, make your own, print it, follow along, whatever you're going to do. So here is something, if you've been in my Math 380 class, Math History, then you will know that there's something called the sieve of Eratosthenes. Eratosthenes is one of the famous mathematicians from way, way back, about the 1400s. And he came up with this. He had a hundreds board basically, and he said, hey, let's talk. I know, first of all, get rid of number 1 because he's not a prime, right? He's neither prime nor composite. We already mentioned that. And I know that 2, interestingly, is the only even prime number that there is. So 2 is the only even prime number, and the reason for that is because any other even number is divisible by 2, right? So we just by definition, it's even, so it's divisible by 2. So that means I can get rid of all of these things, and when you have a nice pretty hundreds board that goes like this, I can get rid of all of the things that are in these columns, right? So it's really nice. All the 2's go away except for the actual number 2. All the 4's go away. All the 6's go away. All the 8's go away. All the 10's go away because all of those things would be divisible by 2. So therefore, just by definition, they are not prime because they're divisible by something other than 1 itself. 1 and itself. So the number 2 is a prime number. It's the only even. Okay? So the sieve of Eratosthenes, the way it works is any number that I come upon next that hasn't been marked out is also prime. So, for instance, 3 comes up right next, okay, next to it. And we happen to know 3 is the first odd prime number. It is divisible only by 1 in itself, 1 and 3. So now I need to get rid of anything that is divisible by 3. So you can count if you want to. 1, 2, 3, 1, 2, 3. 6 is already gone, right, because it was even. 1, 2, 3. Oh, look, 9 went away now. 1, 2, 3. 12 is already gone. 13, 14, 15. That one wasn't gone yet. 16, 17, 18. 18's gone. 19, 20, 21 wasn't gone yet. So you can count along if you want to. And we're pretty good with, hey, that's a multiple of 3, right? So it's a number that can be divisible by 3. That's what a multiple of 3 means. But if you pay really close attention as I mark through these, there is a cool pattern that starts coming out. I think I'll do one more and then we'll see it maybe. The really cool pattern is that all of the multiples of 3 on this particular hundreds board are on diagonals. So we're going to keep 3. Sorry, that got kind of dark. But then if I just go down 1, 2, 3 and mark this diagonal right here, all of those numbers were multiples of 3. You can see I already marked them out, right? So I don't have to continue counting up to 100 here. I can literally just come in here and go, hey, all these things on this diagonal, those are going to be multiples of 3. So 63 we can tell was, 81 we can tell was, if you're not sure, divide it out. You'll see. So here I've got this 30 diagonal started. Okay. If you're not sure about 57, let's check it really quickly. Hopefully some of you know the rule for divisibility by 3. If not, we're going to get into it in a little bit so you'll see it. So 5 plus 7 is 12. The rule for divisible by 3 is something is divisible by 3 if you add its digits and the sum is also divisible by 3. And again, divisible means that it will divide evenly into it, right? No remainder. So here we go. I was doing 57, right? So 57, I would take it and go 5 plus 7 is 12. And I would look at 12 and say, hey, is 12 divisible by 3 evenly? And the answer is yes. And by the way, if you're not sure, you can reuse your divisibility rule again. So let's look at that. How does that look? So 12 is 1 plus 2 equals 3 if I add together its digits. And 3 is the number 3, so certainly it is divisible by 3. So because that 3 is divisible by 3, so is the 12. And by the way, so is the 57. So if you weren't sure, you can kind of check and see. Okay, so we're going to skip 2 diagonals, come down here to the 60 diagonal. 60, 69, you can see some of them already marked out. If you're not sure, again, 8 plus 7 is 15. So for sure, 15 is divisible by 3, so 87 is divisible by 3. And then the 90 diagonal, 99. I picked up a couple of extras, right? All right. So you can see what's going on with this. I have a kind of finished product. We'll look at it in a second. The directions are down here. Mark out all numbers that are divisible by the prime numbers that are less than them. So again, I'm looking at, for instance, 25. Whenever I get up here in a second, 25, I'm looking for prime numbers that are less than 25. Well, the 5 will be, and hey, 5 goes into 25 evenly, so therefore 25 is not a prime number. In fact, we know that all of the numbers in the 5 column are divisible by 5, so those are all going to have to go away. So 5 gets to stay, but none of the others in that column. And then look over here, the rule for divisible by 5 is it ends in a 5 or a 0. All the zeros are already gone because they were divisible by 2, so that guy's already gone, so now we've got 5 as a prime number. And then we just keep on going through and working our way through. The next one, of course, is 7. Okay, so a question I had whenever I was looking at this is how do you know you're finished looking for factors of a particular number? How do you know if a given number is prime or not? So there is kind of a little bit of a cheat. I'll show it to you in a minute. But for instance, how do I know that none of the prime numbers that were less than 7 would divide into it? Well, of course I can divide by 2, it doesn't go evenly. Divide by 3, it doesn't go evenly. Divide by 5, it doesn't go evenly. And that's fine on 7, but sooner or later I'm going to get like, what about 1001? Do I know if 1001 is prime or not? Oh my gosh, I don't want to check every single number less than 1001. So how do I know what I can do there and what I can't do there to finish up? So that's my question. All right, so I have a little bit of a nicer version of this over here. Again, I highly recommend that you kind of do this sieve of Eratosthenes yourself, and you'll see the hundreds board come in handy a couple of times in the future. So, looking here, we have 2, 3, 5, and 7. Everything else has been marked out. 11 and 13. 17's prime, by the way, so I'm going to highlight him. 19 wasn't marked out. 23, 29, and 31. Skipping. 37. I believe 41 is prime. I know it kind of looks like I marked it out, but it was supposed to be that diagonal. I got off a little bit. And 43. So I'm like, how do I know? For instance, let's check 43. How do I know if 43 is really a prime number or not? Because it could be that I just haven't gone through enough and seen. So let's check. So my question becomes, is 43 prime? And there's a really cool little check for this. It's called use the square root. So square root of 43. Okay. I don't know exactly what that is. I know that 43 is not a perfect square, so I can't come up with it right off the bat. But I like to do kind of the sandwich method. It works really well for me. For instance, I know that 36 is less than 43. So let me put him in a square root. And I know that 43 is less than 49. Okay, so I'm picking those numbers because 36 is 6 squared, right? So this becomes a 6. I still don't know what 43 is, but 7 squared is 49. So I picked numbers that I knew fell right around 43 that I could easily reduce. Those guys I know. I know square root of 49, so I'm going to use them. I don't know square root of 43, but now I can kind of go, oh, hang on a second. 43 is somewhere between 6 and 7. Square root of 43 is. So it's 6 point something. I don't know what it is. I don't really care. You can go on your calculator and type that in, and I guarantee you're going to get 6 point something. Okay. What's important to us is the whole number part. That's why I don't care what's back there. It's probably like a 6 or a 7 or something like that. I don't care. I care about this whole number part. So here's what we do to check if a number is a prime. Take the square root of that number, and I'm going to use n as any number. Okay, I'm just going to use n as my variable. Okay, so take the square root of that number. Okay, check all prime numbers that are less than or equal to the square root of n. If none of them are factors of n, then n is prime. And clearly, if they are factors of n, then n is not prime because it has more factors than just one in itself. Okay, so check all of the prime numbers that are less than or equal to n. This is important because what if my number had have actually been 36? The square root of 36 is 6. It would be exactly. So I need it to be less than or equal to square root of n. Check all of those numbers, and if none of those primes, checked, are factors of n, then n is prime. Okay, so that's a really cool kind of rule because what that means is if I want to know if 43 is prime or not, I don't have to check every number. So don't check all numbers through 42, right? I don't have to do that. Because now I know, hey, I'm looking for prime numbers that are less than or equal to 6. So instead, I'll check what are my prime numbers that are less than or equal to 6. 2, 3, 5. The next one would be 7. That's not less than or equal to 6, so I stop. So actually, that's only 3 numbers I have to check. The reason for that is that whole thing that we saw in the locker problem. If a number were, like I said, if 36 were a perfect square, if I was using that number, then it would have the 6 in the middle. That would be the pivot point. If not, then one of the primes that are less than 6 would have fit in there, right? Would have factored nicely. So it's that pairing off thing. If it doesn't pair off, then I'm good. So let's check 2, 3, and 5. So does 2 evenly divide 43? Well, no, because it's not even. Does 3 evenly divide 43? Well, now I can use my little cheat, right? I've got that rule that I know. 4 plus 3 is 7. So because 7 isn't divisible by 3, then 43 isn't divisible by 3, right? Oh, sorry, this silly computer's trying to lock up on me. Okay, so if and 3 is does not go into 7 evenly, so 43 is not divisible by 3 either, so that's a no. Okay, and then last but not least, does 5 evenly divide 43? And again, 43 does not end in a 5 or a 0, so that's a no also. So none of these work, and so therefore 43 is prime. Okay. So that's actually a really interesting and very important rule for me to figure out, because as I'm going along, I need to think just a little bit about that. So I already checked the 5s, right? I already checked all the 5s. What I haven't checked yet is the 7s, so we need to think a little bit about that, make sure I didn't mess anything up here. The square root of 100 is 10, right? Which means I need to check all the prime numbers. If I'm checking for 100, I need to check all the prime numbers, 2, 3, 5, and 7, because those are the ones that are less than 10. I shouldn't have to check 11s, because all of those should have already been marked out by something else, and we'll check that in a second. Actually you can see that I've already got it going here. So the 11s would be all these double digits, 22, 33, 44, 55, and you can see that those are all marked out except for the 77 so far. So I really do need to check the 7 because there are some in there. So let's check 7 real quickly. And there is a rule for divisible by 7, but I never remember it, so we can just kind of go with it. So 7, 14, 21, 28, all those are already gone. 35, 42 was already gone. 49, so I wouldn't have gotten 49 if I didn't check 7, right? So he needs to be gone. But after 49 would be what? 56, 1, 2, 3, 4, 5, 6, 7. Yeah, so 56 is there, and then next would be 63, and then next would be 70, and then next would be 77, and I wouldn't have gotten 77 if I hadn't have checked by 7s, right? Next is 84, and next is 91, and next is 98. So I wouldn't have gotten those if I didn't check. Yeah, so I had to check the 7s. But you can see all of the 9s were already gone. Or, I'm sorry, all of the 11s were already gone except for 77. So I had to check for 7s, but I don't have to check for 11s. I shouldn't have to check for 13, so you can check it and see. 13, 26, what would come next? 39's already gone, and then what, 52's already gone, and then 65, I think. So you can just see the pattern going on. All these guys are already gone, so you don't have to worry about them. So that means that any of these other numbers that are not marked out should be prime. So you can double check and see. I'll double check later and make sure. I didn't double check before I walked in here, sorry. Alright, so the question becomes, what about 101? I've got that down here. What about 101? Can you check it real quickly and see? So I want to know, is 101 prime? Because it's off my hundreds board, so that's why I want to check it. Is 101 prime? If you're using this technique, you should take the square root of 101. I don't know what that is. I know it's 10 point some stuff, right? It's like, actually I do know what it is. I wrote it down earlier, 10.05. So what prime numbers do I need to check? Yep, everything that's less than or equal to 10, well 10's not prime, so I need to check 2, 3, 5, and 7. So I'm going to leave it up to you guys to check 2, 3, 5, and 7. You should be able to do the first 3 pretty quickly. 101 is not even, so it's not 2. 1 plus 1 is 2, so it's not divisible by 3. It doesn't end in a 5 or a 0, so it's not divisible by 5. So you should be checking 7. Even if you have to come out here to the side and divide it out, 101 divided by 7, that's so much faster than checking all the numbers that are less than 101, right? So let's just check it real quickly. Hopefully you've done it by now. I gave you a little time. So we know that 7 goes into 31 4 times. That's 28. With a remainder of 4. So does 7 go into 101? No. So you can check all the other stuff if you want to. Check prime factorizations. See if 101 is divisible by 11. See if 101 is divisible by 13. But I'm telling you, you don't have to do all that. These are the only 4 you had to check. And none of them divided into 101 evenly. So 101 is prime. So for funsies, if you wanted to, you could go check 103 because it's the next prime, or it's the next odd number after 101. So check and see if 103 is prime, just for funsies. All right, there we go. So on my handy dandy sheet that I have here, I have written a couple of things. How do you know if something's divisible by 3? How do you know if something's divisible by 5? I talked about the rules. We're going to look a little more in depth at the rule for 3 in just a second. I'm going to do that right now. But I wanted you to actually see a little bit of math history here. If you've ever seen the movie A Beautiful Mind, John Nash is the mathematician who's in there. He tends to be on a little bit on the crazy side if you haven't seen it yet, but it's a manageable crazy at times. So he talks in that movie about twin primes, and it's a really cool mathy concept, something fun. Students tend to enjoy it. So what in the world is a twin prime? Twin primes are 2 primes, thus the twins, are 2 primes that are separated only by an even number. Right? And that should make sense because 2 and 3 are the only 2 primes that are side by side, right? They're never going to be even two side by side because there's never an even number after 2 that's a prime. So there's always going to be an even number in between them. So I see a couple of those situations coming in here. I'm going to mark them. 3 and 5 are separated only by an even number. 5 and 7 are separated only by an even number. And then I go along a little bit, and then here's 11 and 13, and 17 and 19. And then I go, wait a minute, I kind of got stuck. There's not a lot of them here. So I go, oh, wait, I see my next one's 29 and 31, right? And then skip, but there's a couple, 41 and 43. So I can see these pairs that come up from time to time, and then I'm skipping, and I go from 43 all the way to 59 before I see the next pair. 59 and 61. So I can start seeing these twin primes coming in, but they seem to be spacing out more and more. Like I had several right at the beginning, and then there's a gap, and then there's a bigger gap, and a bigger gap. So there are some conjectures out there, and some of them can be proven and some of them can't. So there's a twin prime conjecture. First of all, there's a prime number conjecture that says there's infinitely many prime numbers. You can't find the biggest prime number, is the way that goes. And then there's another one that says these twin primes go on forever also. So for instance, we can see way up here 71 and 73. There's a set of twin primes, but it's starting to get farther and farther apart. So you would have to go do a little bit of research on that, but it's kind of a cool thing. It's in a movie, so that makes it fun. And sometimes students, younger students, really enjoy playing with those in sand. Okay, so I need to talk to you really quickly about this rule for divisibility by 3. Okay, because a lot of people say, okay, I know that rule. I know that, you know, if I want to know if 57 is divisible by 3, I know that I add 5 plus 7 and I get a 12, and 12 is divisible by 3, so therefore the entire 57 is. But why? And the answer is, this is a result of our unique base 10 system. Okay, so that's really, really important as you talk to kids and see what's going on. It doesn't always happen this way, but because we're using the base 10 system, I can say, hey, let's look at all of our place values in base 10. So we have the ones position, and we have the tens position, and we have the hundreds, and we have the thousands. And you can keep going, but I just want to deal with these so we can talk about them. So something interesting that happens about any of these base 10 positions is if I look at them, let me start on this end actually. If I look at them, they are always a multiple of 3 plus 1. So again, multiple of 3, we didn't quite talk about multiple yet. A multiple is a number that has the given number as a factor. Okay, multiple is a number that has the given number as a factor. So in this case, I'm talking about 999. 999 is a multiple of 3 because 3 goes evenly into it with no remainder. So 3 times what gives me 999? Okay, it's 333, right? Okay, so 999 is a multiple of 3. We can see that. So what I'm saying about 1000 is it's 999 plus 1. Does everybody agree with that? Okay. And then over here, I can do a similar thing. 99 is 3 times 33, right? So 3 times 33 means that 99 is also a multiple of 3. So I can go 99 plus 1. Okay. So last but not, well, not last but not least, I'll get back to you in a second on that. So this is 9 plus 1. And we all know that 9 is 3 times 3, so I think we can agree that 9 is a multiple of 3. And then last but not least, let me just write that up here just to make sure everybody agrees. It goes in evenly. Last but not least is this guy 1 here. So it's actually going to be 0 plus 1. Let's think about that. First of all, everybody agrees 0 plus 1 is 1, I think. But let's think about how that works. 0 equals 3 times 0. So even though 0 is not bigger than 3, so you got to watch out because sometimes people will say, oh, a multiple is the bigger number. Normally the multiple is the bigger number, but not always. So even though it's not bigger, 0 is a multiple of 3 because 3 times 0 gives me that. So interesting factoid. I already know 999 is divisible by 3. And I already know 99 is divisible by 3. And I know 9 is divisible by 3. And I know 0 is divisible by 3. So whenever I get rid of those, because I know all of that is divisible by 3, what's left over are the ones. So for instance, if you tell me that, let's go back up here to 57. Let's pull him apart and say what is 57. If I look at 57, 57 is equal to 50 plus 7, right? Okay. But when I look at that, that means that that's 5 sets of 10, right? So I could also say that's 5 sets of 9s plus 5 sets of 1s. Does everybody agree with that? 5 sets of 9 would be 45. Well, hang on. I know that's divisible by 3. Right? So we can kind of ignore that for a second. And then 5 sets of 1 right here. Well, that would just be 5. So what I'm worried about is 5 going to add together with some other weird number here in a second and make it so that, there we go. Is 5 going to make it so that I can add it with some other number and that the individual leftovers, so to speak, will work out? Well, 7, wait, that's 7 times 0, right? Which is just 0, but that's divisible by 3. I don't have to worry about him. He can go away. And then plus 7, right? 7 times 1 or 7. So it's those leftovers that I have to worry about. Because the people who are divisible by 3 anyway, any multiple of something that's divisible by 3 is divisible by 3. So in other words, I know that 3 goes into 9, and therefore because 3 goes into 9, it will also go into 45, right? So that I don't have to worry about. What I have to worry about is the leftover pieces. So each little leftover piece is one little guy here. So that's why I can say, hey, 5 leftovers plus 7 leftovers. If I can combine all those leftovers together and get me some number that's divisible by 3, hey, I'm good. Another way to look at that, let me just show you really quickly. If you've done base 10 blocks before, I'm going to still use my same example. If you've done base 10 blocks before, maybe that helps you see. So 50 is 5 longs, right? And 7 is just going to be 7 singles. I'm lazy, I draw circles. Sorry about that. Okay, so if I look at that in that whole, each of those 10s is 9 plus 1. That means there's one little guy. These are 9. We know that's divisible by 9. But there's one little guy left over out of each individual long, right? This guy, the 9 is going to go away. This guy, the 9 is definitely divisible by 3. This guy, we don't have to worry about that 9. And this guy, who cares about that 9? Those 9s are all divisible by 3. So when I talk about leftovers, what I'm saying here is that I've got all of these leftovers. I can draw those down here. 1, 2, 3, 4, 5. And then I've got these units, 7. And when I count all that up, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, wait, I could group those into 3s, right? So if I can group everything into 3s, then that means the entire thing is divisible by 3. And if you still don't believe me, then what you can do is you can take all your 5 longs and you can break all of those down into units. So you would have 50 little units running around there and group those up into 3s, and all you'll have left over will be 5, and those will match up with these 7. So again, my leftovers are 12. And those are groupable into 3s. That's what I'm telling you. It's really pretty cool when you think about it like that. All right? So whenever I start talking about this, we look at it, we say, hey, that's the divisibility rule for 3s. You can work that out. There is a divisibility thing that I'm going to put up so for you. It's going to be your homework for you to look at. And in addition to that, so this will look like this. Divisibility rules. It's all about 3, so hopefully you followed what I just talked about. And then there's also the thinking about factors that I warned you about earlier. So those will be homeworks for day 1. All right. That's it for day 1 of week 2. Good luck, and I will see you on day 2.